Okay, so in the previous video we proved all four of these things, that cos A minus B equals cos A, cos B plus sin A, sin B, etc. What we can do is we can use these results to then prove the final two main identities we need, the addition formulas, tan A plus B and tan A minus B. So if I start with trying to find tan A plus B, yeah, I need to recognize that this is sine A plus B over cos A plus B, yeah? And then from here I can use my results from, well, I'm looking at number 3 and I'm looking at number 2. So I can say that tan A plus B equals, well, sine A plus B is sine A cos B plus cos A sine B all over cos A cos B minus sine A sine B, right? So for tan A plus B, I want my stuff in terms of tan, okay? So I need to get these in terms of tan somehow. So I'm going to divide every single thing here by, if you see I've got a sine here, so I need to have a cos on the bottom, don't I? And I've got a cos here, so I need to have the cos on the bottom as well to correspond, so I get a tan here, and I need a tan here. I want to get all this, I want to get rid of these sines and coses, so I'm going to divide all by cos A, cos B. So this implies that tan A plus B equals, always equals, sine A cos B over cos A cos B plus cos A sine B over cos A cos B. So every term is being divided by cos A cos B, and minus sine A sine B over cos A cos B. Now from here I can see that this cancels to 1. This cos B and cos B cancels to 1, and this turns to tan A. This cos A and cos A cancels to 1, and this turns to tan B. And finally, these two are the sum of tan A and tan B. So I can say that tan A plus B is always equal to tan A plus tan B all over 1 minus tan A times tan B. So this is our fifth core identity, or fifth core addition formula. So now I've got this result, I can do similarly, just like I did with cos and sine. I can now find the opposite by saying, so the opposite sign, so I want tan A minus B identity this time. Tan A plus minus B is always equal to, so again, tan A plus tan minus B all over 1 minus tan A tan minus B. So this means that I get tan A minus B is always equal to tan A. Tan of minus B, because it is not an even function, means that f of minus x equals minus f of x, so this turns to a minus tan B all over 1 minus, but it's not a minus anymore because again I have this tan minus B so that would make it a plus tan A tan B. And there we go, we have the final addition formula. Okay, so there are some key double angle formulas that you need to know. The first one is sine 2x, and I know that sine 2x is always equal to 2 sine x cos x, so that's an identity right there. Now, the way I know that is through using the double angle formula. So if I'm looking at sine A plus B, so guys, this is what you need to know, this is what you need to remember, and you need to remember the double angle formulas as well, okay? Not how they're proved, but I'm going to prove now how this is actually the case. So I've got sine A plus B is always equal to sine A cos B plus cos A sine B, which was the result we proved before. Here, I've got 2x, haven't I? So I could say that I could say let A equal x and B equal x. So I can say I have sine x plus x equals sine 2x, doesn't it? 2x. So therefore I can say that this is always equal to them, with taking A as x and B as x, I have sine x times cos x plus cos x times sine x. So therefore I can say that sine 2x is always equal to this plus this, 2 sine x cos x. Now I can move on to the cos 2x and proving the cos 2x. This is slightly more difficult, guys, because cos 2x actually has 3 identities within it. Okay, so this is the main one that we can prove using the addition formula, and then we can use our other identities, namely being sine squared plus cos squared is always equal to 1, to manipulate this to look slightly differently. So we'll have 3 versions of cos 2x. But let's prove where this initial one came from then. So I know that, just like before, cos A plus B equals cos A, always equal to cos A cos B minus sine A sine B. So again, let A equal x and let B equal x implies cos x plus x, which of course is cos 2x, is always equal to, replacing my A and B by x and x, cos x minus sine x sine x. So therefore I can say that cos 2x is always equal to, that's cos squared, that's sine squared, cos squared x minus sine squared x, as required. So like I said, guys, this is your first main identity, which is proved by this formula here. But now, so let's call that version 1. Now I can say version 2, that cos 2x is always equal to, from my sine squared x plus cos squared x is always equal to 1, I can say that cos squared x is actually 1 minus sine squared x minus sine squared x. So therefore cos 2x always equals to 1 minus 2 sine squared x. So there's my second version right there. And similarly, I could show my third version, by saying that cos 2x, going back to this cos squared x minus sine squared x, the first one, if I this time replace this by 1 minus sine squared x, so sorry, 1 minus cos squared x, then I'll get another result. So I get cos 2x is always equal to cos squared x minus 1 minus cos squared x, from our identity here, yeah, that we learnt in C2, implies that cos 2x is always equal to, well, this is cos squared x plus cos squared x minus 1, so 2 cos squared x minus 1. And there we go, that's version number 3 proved. So you can see we've got 1, 2, 3 versions of the same formula. I recommend that you do commit those three to memory. And the last double angle to prove then is this tan 2x is always equal to 2 tan x over 1 minus tan squared x. So again, if we go back to my double angle formula, tan a plus b, my addition formula, my tan a plus b is always equal to tan a plus tan b over 1 minus tan a times tan b. Again, let a equals x and b equal x implies that tan x plus x, which of course is tan 2x, is always equal to tan x plus tan x over 1 minus tan x times tan x, which gives me my tan 2x is always equal to 2 tan x over 1 minus tan squared x. And there we go. We've proved all the main identities so far that we need to know in terms of double angles and the addition formula. Now, with this new knowledge then, I can work out my original problem, so what cos 15 degrees is without a calculator. So I can say that this is cos 45 degrees minus 30 degrees, and therefore use my addition formula. So I can say this is cos 45 cos 30 plus sine 45 sine 30, which it means that I have cos 15 degrees is always equal to, well, cos 45, not even always equal to, is equal to cos 45 is 1 over root 2, cos 30, special triangle is 60, 30, 1, so cos 30 is root 3 over 2, plus sine 45 is 1 over root 2, again for my special triangles, and sine 30 is a half. Therefore, I get cos 15 degrees, that's rubbish, that doesn't look like 15 at all. Cos 15 degrees equals, well, I've got root 3 over 2 root 2 plus 1 over 2 root 2, so this is root 3 plus 1 over 2 root 2. I could rationalise the denominator by timesing them both, top and bottom by root 2, so I get root 6 plus root 2 over root 2 times 2 is 4. And similarly I can say, well, I can now prove this proof. If I take the left hand side, I get sine x plus y over cos x cos y equals sine x cos y plus cos x sine y all over cos x cos y, which then, if I split this up, sine x cos y cos x cos y plus cos x sine y over cos x cos y, I can see straight away these two cancel to 1, this would make tan x, and these two cancel to 1, and this would make tan y, so this equals tan x plus tan y, 3 lines, right hand side, as required, pretentious box.